Hello students, in the last video we were discussing how to find the ratio of specific heats, that is gamma Cp by Cv of a monoatomic gas. So today we will be doing how to find the ratio of specific heat for a diatomic gas, triatomic gas and for polyatomic gases. So let us first see how to find the ratio of specific heat for a diatomic gas. A rigid diatomic gas means there will be translational motion as well as rotational motion. And I discussed in the last video, if there is a translational motion and rotational motion, there will be 3 degrees of freedom for translational and 2 degrees of freedom for rotational. So altogether 5 degrees of freedom. So a diatomic molecule consists of 5 degrees of freedom. And according to law of equipartition of energy, energy per degree of freedom is how much? Half kBt, right? Energy per degree of freedom is half kBt. So what is the energy for 5 degrees of freedom? 5 by 2 kBt. 5 into half kBt, that is 5 by 2 kBt. So we got the energy. Now what you have to do? Energy for 1 mole. This is energy for 1 molecule. Now to find energy for 1 mole of gas, what will you do? 5 by 2 kBt into Na, Avogadro number, and Kb into Na is universal gas constant, capital R. Kb into Na is R. So instead of Kb into Na I put R, so I got 5 by 2 RT. So this is total internal energy of 1 mole of gas. Now we have to find Cv and then Cp, then the ratios. So how will you find Cv, specific heat at constant volume? Du by dt. I have to differentiate this. So here when I differentiate, dt by dt becomes 1. So I will get 5 by 2 R. Now we already know Cp minus Cv is R. So how will I find Cp? Cv plus R. Cv is 5 by 2 R. 5 by 2 R plus R, 7 by 2 R. So I got Cp and Cv. Now Cp by Cv is gamma. Therefore gamma is equal to, I divide both, I will be getting the answer as 7 by 5. So Cp by Cv is 7 by 5, or when I divide it, I will get 1.4. So you can either write 7 by 5 and it is equal to 1.4. In the same method, you can derive the expression for the ratio specific heat for triatomic gas if they ask. Triatomic can be linear triatomic or non-linear triatomic. So they will specify in the question whether to write linear or non-linear. Okay, so you can proceed in the same way and get the answer. Now for a polyatomic gas, specific heat for a polyatomic gas. The polyatomic gases will have 3 translational degrees of freedom, 3 rotational degrees of freedom and F number of vibrational modes. So we don't know how many vibrational modes. See, the total internal energy of 1 mole of gas can be written as 3 into half kBt, that is translational degree, plus 3 into half kBt, that means rotational, plus F into half kBt, that into Avogadro number. So here it is 3 by 2 plus 3 by 2 and here it is F. Kb I am taking everything outside. Okay, Kb I take outside, so Kb into Na is R, that is how I got R. So the remaining thing is 3 by 2 plus 3 by 2 plus F into RT. Therefore 3 plus F RT, that is the equation. Now when I take Cv, Cv is du by dt as we told already. So when I differentiate this, dt by dt becomes 1, so I will get 3 plus F into R. Then Cp can be Cv plus R. So 3 plus F into R plus R. So 4 plus F into R. And gamma can be written as Cp by Cv. So 4 plus F divided by 3 plus F. So like this you can find the specific heat capacity of a polyatomic gas. Now if I consider the total degree of freedom as F, I can give you a shortcut equation for finding gamma. Gamma can be found by 1 plus 2 by F, where F is the total number of degrees of freedoms. Total number of degrees of freedoms. In the previous one, I took a F as a number of vibrational degrees. If they give the number of vibrational degrees, we can find it like that. So I am not taking F here, I take G. Let it be G. G is the number of degrees of freedoms. So for monoatomic, molecule, degrees of freedom, it is better to take degree of freedom as D. So for monoatomic, degree of freedom is 3, right? So gamma is equal to 1 plus 2 by 3, that is 5 by 3. Now for diatomic, D is equal to 5. So gamma is 1 plus 2 by 5, 7 by 5. Now for linear triatomic, D is equal to 7. So gamma is 1 plus 2 by 7, 9 by 7. For non-linear triatomic, D is equal to 6. So gamma is equal to 1 plus 2 by 6, that is 8 by 6, which is 4 by 3. Like this, using this equation, you can find the gamma ratio specific heat for all the molecules. Okay. Now there is one more topic left for us, mean free path. We know the molecules are always in random motion, and these molecules will collide with each other, and also they will collide with the walls of the container. The molecules will collide with each other, and also they will collide with the walls of the container. So if we say the path between two collision, that will be a straight line. For example, one molecule will go in a straight line and collide with the other molecule. Then only after collision their path changes. So the path of the molecule change here again, and then it collides with the next molecule. Again the path changes. So the path is a straight line till collision occurs. Since the motion is random, sometimes collision occurs fast, sometimes collision occur after some distance. So the distance between two collision keeps on changing. So the paths traveled by the molecule in each collision will be a straight line, and that path is called free path. And you can see this free path is different for different collisions. Sometimes the path is short, sometimes the path is big. So if we take the average of all these collisions, that is called mean free path. So mean free path is the average distance between the two successive collisions. So inside a gas there are several molecules, they are in random motion. The distance which a particular gas molecule travels without colliding is known as mean free path. So, I have just shown the path of one molecule. Okay. So, each path is different, that is called free path. The average of each free path is called mean free path. Got it? Now, there is one equation for finding the mean free path. Mean free path is written as lambda bar. We do not have to study the derivation, we only have to study the equation. So, mean free path is given by lambda bar, which is kBt divided by root 2 into pi d square p. This is the equation for the mean free path. So, there is no derivation to study, just one equation, and just take down what all quantities are representing. Lambda bar is called mean free path, Kb is Boltzmann's constant, T is absolute temperature, P is pressure, and D is diameter of the gas molecule. Okay. So, with this our chapter comes to an end. Remaining things of the chapter are deleted from our portions. So, we have only this much to study. So, with this our chapter comes to an end. Thank you.